Okay, so this is Algebra 2 review, 2025 spring. I've got a young Mr. Joey here. Joey, say hi to YouTube.
Hi.
Okay, Joseph, we already did some of this stuff in class, and you know a lot of things, which means we're probably only going to cover the tough stuff. So, Joey, where do you want to start?
Can we do on 11?
Yep.
This is the one I really don't get this kind of rationalizing numbers.
Yeah.
That's like that. I think that's the
Yeah, this thing's a little weird. So what we want out of these problems down here, 1141, 1142, like these guys, right? What we're trying to do here is we are trying to get rid of the radical in the bottom, which is an irrational number. Like root 3 is 1 point blah, 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 blah. We don't want that because dividing by 1 point blah, 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 blah is hard to visualize in our heads. It's much easier to multiply by that. So what we're going to do is not change the number, which means the only thing we are allowed to do is multiply by 1. Does that make sense, right? Otherwise, we're changing things. You could also add 0, but that's not going to do too much. So there's lots of versions of 1 we can multiply by, and the idea is if I multiply by root 3 over root 3, that won't change the number because root 3 over root 3 is 1. And what I'll end up with is 5 root 3 in the top, and the bottom I'll get the root of 9. Now what is the root of 9, Joseph? It's 3. So 5 root 3 divided by 3. So this is quote-unquote easier to think about. 5 times 1 and change is like, I don't know, 6, 7, 8, something like that, right? And we're dividing that by 3. So 8 over 3 is about what this is approximately equal to.
So you just want to get rid of the bottom.
That's it. That's it. Now, it's pretty easy when it's a square root because you just multiply by itself, and of course, then you get 9, which is a rootable number, right? But when it's not a square root, like a 9th root, things get a little bit trickier. So if I just multiply by the 9th root of 2, top and bottom, I get the 9th root of 4. Is the 9th root of 4 a nice number? No, right? So here's the big brain play. We're actually going to multiply by the 9th root of whatever 2 to the 8th is. We could calculate that if we wanted to. I think it's like 64 maybe. Oh no. Why no signal? Check 1, 2. I'm good here. Why am I not good here? That. My computer's killing TVs. Is that what's happening right now? Something. Okay, cool. All right. So hopefully that just stays the rest of the time, no issues. So what we're going to do is multiply by the 9th root of 2 to the 8th, whatever that is, right?
Where is the 8 from?
The 8 I'm getting from this. I know that when I multiply these, I get the 9th root of 2 to the 8th times 2. Well, that's just 2 to the 9th, isn't it? That makes sense? What is the 9th root of 2 to the 9th? What number do you times by itself 9 times to get 2 to the 9th? Nope. I want to say it again. I want to say it slowly. Here it says, what number do you times by itself to get 9? 3, right? Here it's asking, what number do you times by itself 9 times to get 2 to the 9th? Just 2.
No, I mean it's like the 8th power.
Where I got the power here?
Yeah.
My thought is, if I have a 9th root, I need something to the 9th here so it roots nicely. Just like when I have a square root, I need something squared so it roots nicely.
So, because the 2 is one number and the 8th is another number?
Correct. So we have 2 to the 8th times 2 to the 1st, which is the same thing as 2 to the 9th. And the 9th root of a 9th power is just this, right? That's the idea, except you can't see it. Just 2. There we go. Apparently this screen over here that I'm recording is wider than the one that you get to see. That's fun. So that's where I got that number. Now, in order to complete this problem, I have to do it same top and bottom. 1 times that is just, well, whatever this is, right? And there we go. Now I'm going to do another example real quick. So if I had, and we'll use a big marker so you can see it nice and easy. If I have, and we're zoomed in, so I'll zoom out. Something like 1 over, let's see, let's do the cube root of 4. Now, is 4 a nice number to cube root? Remember, cube root is asking what times itself 3 times gets me 4, right? It's not. But if I were to multiply by the cube root of 4 squared. What I'm going to get is the cube root of 4 times 4 times 4. That's 4 cubed. What's the cube root of 4 cubed? 4, right? Right? What number do you times by itself 3 times to get 4 cubed? Well, 4 times itself 3 times gets you 4 cubed. So that's the big brain play. That's where I get that 2 from. I've already got one of the 4s here. If I get 2 more of them, well, I've got 3 total. Cube roots and cubes cancel out, right?
So, basically what you're essentially doing is, basically it's like the answer.
Mm-hmm.
It's just the bottom number, the denominator, what's the bottom number?
Yeah, denominator. Yeah.
The denominator is by itself. On top of it is what was basically essentially the bottom.
Yes, because timesing by 1 is what I'm doing here, right? Which won't change the number. So this is the exact same number as this. But people say this is quote-unquote easier to work with. I have some debate with that, but you need to know how to do it and simplify, right?
I'm just putting it on top.
Yeah, we want the roots to be on top. We don't mind roots on top. The problem is radical denominators, right? So deradicalizing the denominator is going to get us over there. Oh boy, it's going to be doing this, huh? Okay, questions about that? Would you like to see another example?
Could we try the level 4 how I like the
Down at the bottom?
wait?
What are you saying? Which ones?
The bottom.
These guys? Yeah, absolutely. So these guys are tricky because there's 2 terms on the bottom, right? So if I zoom in on this guy, what I'm going to do is I'm going to multiply by the conjugate. And the reason I'm going to use the conjugate is because when I multiply by the conjugate, basically what you get is a difference of squares, right? So I'll get 5 times 5, which is 25. I'll also, when I distribute, get 5 root 2. Now that's a problem. That has a root in it, right? However, because I'm multiplying by the conjugate, I'll also get negative 5 root 2 here. And that goes away, doesn't it? Multiplying by the conjugate gets rid of the middles, right? Yeah. And then root 2 times root 2 is the root of 4. It's going to be negative, right? Negative root 4. And that could be a problem, except what is the root of 4? It's 2. So this bottom simplifies to 25 minus 2, which of course is just 23. I get 10 plus 2 root 2. Yeah, all over 23. And it's deradicalized. So that's the idea there. So when there's multiple terms, multiply by the conjugate. That way you get rid of that problematic middle. And you'll notice what happens is we get 5 times 5, which is 25, and root 2 times root 2, which is root 4. It's guaranteed to get rid of the root.
It makes a lot of sense now.
Yeah, right. I figured it would. So over here, same thing. 2 terms. If you times it by itself, you're going to have middles, right? So what we're going to do is multiply by the conjugate, top and bottom. 1 minus 5 root 3 over 1 minus 5 root 3. And the top's not really interesting, right? We'll get whatever it is. But the bottom, we're going to get 1 times 1, which is 1. We're going to get a negative 5 root 3 and a positive 5 root 3, which will go away, right? So all we get left is that negative 25 times the root of 9. Are you seeing that?
So then that just becomes
25 times 3.
that becomes 0.79.
Because root 9 is 3, right?
Yeah.
So we get 1 minus 75. So negative 74. So our denominator is going to be negative 74. I'm sorry, I'm trying to squeeze all this in here so you can see it nice and easy. There you go. So the denominator is negative 74. And the top will be negative 4 plus 20 root 3. And I'll just let you think about that for a second before we go on.
The first two numbers was basically like 1 times a 4 and 5 times a 4.
Correct, yes.
And then it's
Mm-hmm.
add on the root 3.
Yeah. So this term and that term being multiplied by -4. So we have -4 and positive 20 root 3. Now you could simplify from here because all these are divisible by 2, but if you don't want to, you don't have to. I'm not too picky about that.
And you said for the test on the redundant, we can kind of skip it.
Yeah, absolutely. Yeah, if you've got evidence for it, you're good to go. Yeah. So there you go. How you feeling about that? Good. Yeah. Again, big brain play. When it's two terms multiplied by the conjugate, it'll get rid of stuff for you. When there's a single term, well, then you got to be careful about what kind of roots you're dealing with, right? Square roots, okay, cool. We're going to get 9. Root of 9 is a nice root, right? Here, the 9th root of 2 squared would not be nice, right? 9th root of 4. But the 9th root of 2 to the 9th is nice. It's just 2, right? Cool. All right, now we've got 11.5 and 11.5.2. Do you want to skip these? Do you want to look at any in particular on this test, or what? What do you want to do?
I feel good about the rest of it.
Good. And we will have time in class. As you've noticed, it'll be monopolized by people who are like, I want to see every problem, but like, you know. So feeling good about 11, huh? Okay. So on to 12 and 13.
I just grabbed my check sheet so I can see when I'm.
Yeah. Take your time. We got plenty of time, bud. Yeah, take your time.
Because some of these on here, it's just, I know I'm good, it's just, didn't do that much on it.
Right, okay. Well, if you want to double check, we can do that too, but yeah. Whatever you want to do, man.
So for a lot of, like on like the third page,
Okay.
basically, it's most of these just doing quadratic formula, basically.
13.3.1 is, right? Because it wants to use quadratic formula.
So I think it's just use quadratic formula.
13.2.1 says complete the square. So
But whenever I split the square, I answer whatever the answer to my quadratic formula.
if you do the quadratic formula, you'll get the same answer as complete the square, yes. However, I want you to show the complete the square work on these guys. Does that make sense?
What's the complete the square again?
Complete the square is this guy. And once I show it to you, you'll be like, oh yeah. Half of this. That gets me a positive 16, and I don't want that. That's complete the square, right? So what's my answer going to be? Well, let me simplify a little bit. It's going to be x is going to equal 19, except I got to root it, and I got to add 4. Ta-da, there's your answer. Right, if I plug this in, subtract 4 gone, square it gone, I get 19 minus 19 is 0. That's complete the square.
Okay.
Yeah, I figured as soon as I showed it, you'd be like, oh yeah.
My friends, I sometimes I know how to do it, I feel like. I just know when it's asking me to do what.
Words are hard, math is easy. Yep. And if you have questions about that, I can be like, here's what it wants, right? I can translate for you. So quadratic formula is that giant formula where it wants you to plug in A, B, and C.
I somehow, I was struggling so bad with it, then I do an exercise, 11.
Yeah.
I just memorized it.
Yeah.
I figured the second B, the A, B part 8.
Yeah, exactly, right? Yeah. I mean, memorization, it should happen when you use it so often that you accidentally memorize it. And that's what happened to you, right? You just did it on accident. Yeah. Yeah. Getting there is kind of tough too, right? How do you feel about getting the quadratic formula, like deriving it, like starting with ax squared plus bx plus c equals 0 and then moving things around?
Just getting the thing itself up.
Yeah.
I can find that.
Okay, good. Okay.
My only thing is I have to remember sometimes that if I'm starting with negative b, I might have to negatify it.
Yeah. Might make it negative, might make it positive.
I have to add a little extra negative symbol in front.
Yep.
That's what throws me off.
Yeah. So let's do an example real quick. So let's do this one.
It's 2 times a, not 2a squared.
2a on the bottom, yeah. So a is 1, b is -3, and c is -10 in this problem.
We're on B.
Yeah, b. Yep. So if I move this over, r squared minus 3r minus 10, right? So a, b, and c. We got it. Can you read that? Better.
That's it. I can read that fine.
Awesome. So when you do the quadratic formula, it's negative whatever b is. Always use parentheses when you're plugging stuff in. Plus or minus the square root of b squared minus 4, whatever a is, whatever c is, all over 2a. And it's doing that thing again. Awesome.
Is it a good thing to plug in all my if I have like a 1?
If you know that you're going to be okay, you know what I mean, because there's a 1 or something, you can skip it if you want. I like being thorough. If I'm going to show my work, I want to make sure I show it all, because if I make a mistake, then I can go back and look, you know what I mean?
Like where it was made.
Yeah, exactly. So A is 1, which is going to make things super easy, right? So A there, B is -3. So this is where that double negative pops up, right? And that's why it's really good to use parentheses. And then C, the only time it comes up is right at the end, which is -10. And so if we use this, I know it's super blurry over for you, that's going to be a +3 plus or minus the square root of 9 plus, it'll be a plus because that's a -10 over here. So that's +40. Oh, and that's going to be convenient. 2 times 1 is 2. So we get 3 plus or minus the root of 49. What's the root of 49? All over 2. So our two different answers, we can actually simplify this. It's going to be 3 plus 7, which is 10 divided by 2, so 5. That's our first x.
You want us to simplify?
I'm fine if you just do this, but hopefully you can see 3 plus 7 is 10, divided by 2 is 5. The other answer then will be when we subtract. 3 minus 7 is -4. -4 divided by 2, -2. There they are. So this one should have been factorable. Like we go back to the top here, numbers that multiply to -10 and add to -3, we would have got them, 5 and 2,
I think
right?
that might just be my only hesitation for just remembering the factors.
Gotcha, if you need to, yeah. Yep, that's chapter 10 stuff, it's been a while.
Because a lot of times, like, not that, but I would have minus the square root of 49 over 2, and I would just leave it at.
Oh, you mean do the root, you mean?
Yeah, but not go to the 3 plus.
Yeah. You just leave it as 3 plus or minus root 49 over 2. Yeah, I'm okay with that. But try to look out for those things. Like, we know the root of 49. Yeah. Yep, yeah, I'm not going to be like, oh my god, he doesn't know how to do this problem. I'm going to be like, Joey doesn't remember how to do roots, or he didn't notice that he needed to simplify that, right? Can he do quadratic formula? Clearly, right? That's what I care about. Anything else you want to see for 13, chapter 13 or chapter 12? And if you're not sure, you know, we can go and look for some. Oh, this is going to be fun. Seems like there's a short in this cable. That's okay. I've got like 12 others of these ones to try out before tomorrow.
Yeah, I got all basics done for.
Yeah, I figured you would.
And then. I don't think so.
Okay, cool. So then on to 14, the last one.
And I don't at all remember how to do this.
Yeah, no, that's fine. It was very quick that we went over it, so you haven't had a lot of experience. And we haven't had anything assigned, so you haven't had a ton of practice.
So then, like, what are we supposed to use for our check sheets?
Do you guys have a check sheet for 14?
Yeah.
Oh, I get what you're saying. Because you need evidence for that. So you can do problems from the book, or you can do these. This can count as evidence, right? Like, there's lots of different ways.
And like, one or two things.
Yep, totally fine. I don't need a ton. And it's it's 2 sections, and it's really just 2 topics, right? It's really not that much. It's graphing parabolas and it's graphing circles. And 90% of graphing parabolas and circles is completing the square, right? So right now it's hard to tell where the vertex is for this, right? We know it's going to open up like this because it's a y equals x squared, and I'll zoom in so you can see a little bit better, right? But we don't know where that bottommost point is, right? Can you tell what number I plug in to make that y value? Here's the y-axis. to make that y value as small as possible? Probably not, right? But if I complete the square, it becomes really obvious. So I'll do that. I need x minus 4 quantity squared. That's the perfect square. That's going to give me my x squared. It's going to give me my negative 8x squared, or my negative 8x, and it's going to get me a plus 16, right? Which I do not want, otherwise that changes the problem. So when I simplify this,
Oh,
you got it, yeah?
I was confused with plus.
Yeah, from here. Yeah. So this is the exact same thing as the original equation, this down here. But now it's obvious what number to plug in to make this as small as possible. What number should I plug in to make this square as small as possible? 4. Because without imaginary numbers, the smallest thing a square can be is 0, right? So how do I make this 0? Well, when x is 4. So I know my vertex is going to be 4, comma, something. And you can probably tell, well, at least if you can see. Here, do this again. Good thing we're almost done with this, huh? What a nightmare. It'll go to the gym. Use their giant projector. For Algebra 1, yep. So hopefully you can tell, if we plug in 4 for x, what we're going to get for y, the other half of this coordinate. If I plug in 4, I get 0 here, right? 0 squared is 0. What's 0 minus 10? Yeah, negative 10. So that's the y value that I get there.
So because that's 0,
Yes. So whatever you plug in for x, what goes with it for y? Well, it turns out it's that last number, isn't it? Oh, geez. A little too hard, huh? It also doesn't help that we're running all of this on a time. Working its heart up trying to both record this and we're not using my big computer like I used to. I retired that one and bought a little tiny guy.
I never knew you used that.
Yeah, it used to be a huge one over here, like an actual tower. This guy is great for everything I do except this because its graphics card is like super. The other one was terrible for everything except this because it had a graphics card. But yeah, wasn't very good for the other stuff because it was so slow. Processor was old. Makes sense. I bought it when I was in college, or made it when I was in college. All right, so when I plug in 4, right, I get negative 10 for y. So that must be the lowest point on my graph. That's the vertex. So I'm going to graph that. 4, negative 10. I'll zoom out. It'll look awful. 4 to the right, negative 10 down. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's 4, negative 10.
Is that it though?
Not yet. We got to graph it. So what do we know about parabolas? We know the basic parabola is this. Y equals x squared. And every parabola will work just like this if you consider its a value. So look at the a value here. Well, as best you can, Joey. They can see it clearly on here, but not over there. So a is 1, right? So this grows at the normal rate. Remember that from the board work, right? It grows at a normal rate. It opens up.
It is the thing that goes like.
Uh-huh. Yep, exactly. Yeah. So a normal parabola, the basic parabola, when I plug in negative 3, negative 2, negative 1, 0, 1, 2, and 3, when I plug in those points, I'll get 9, 4, 1, 0, 1, 4, and 9. Remember that? Right? 3 squared, 2 squared, 1 squared, 0 squared. Right? That's what'll happen here. Take x and square it. That'll give you the y value.
And they're equal to each other. No.
So what's going to happen?
The x squared is equal.
Y. Yes, that's what this is saying. Yep. And our graph will work just like this. It'll just start in a new location because they both grow at the same rate. A 1 for the a value here. So all we have to do is instead of starting at 0, 0 and moving 3 to the left and 9 up, we're going to start here and move 3 to the left and 9 up. That's it. So moving 3 to the left and 9 up, that puts us here. If you want to label that point, you can. 3 to the left is 1. 9 up is minus 1. Instead of starting at 0, 0 like this one would, this original graph, right? We're going to start at our vertex and go 2 to the left and 4 up. So, yes, basically. These are not coordinates anymore. It's not negative 3 comma 9. It's from wherever you're starting. So this one starts at 0, 0. So its coordinate is literally negative 3, 9.
Okay, because I was confused because it was 1, 1, but there's a negative 1, 1.
Yeah, and it's, yeah, exactly. Yeah, I see what you're saying. Yeah. So negative 3, 9 is what's happening here. That's a crazy coincidence. Yeah, starting here, going 3 to the left and 9 up. Okay?
These move from
from the vertex, yep.
Only from the vertex?
Yep. This one's vertex is at the origin, which is why when we graphed it, it literally, these were the coordinates, right? But this one's vertex is moved, right? It's going to be 4 and negative 10. So it's down here. So for the next one, it says 2 to the left, 4 up. So 2 to the left, 1, 2, 3, 4 up. And if you want to label that point, 2 to the left is going to be 2, and 4 up is going to be negative 6. Then this minus 1, 1, what it means is 1 to the left and 1 up. So that's this dot here. 1 to the left is 3, and 1 up is negative 9. And we know parabolas are symmetrical. So 1 to the right, 1 up, 2 to the right, 4 up, 3 to the right, 9 up is going to be this. Exact same thing, just on the other side. And here is our sketch. And again, you can label all these points if you want. I don't really care. 1 to the right and 1 up is 5, negative 9. 2 to the right and 4 up is 6, negative 6. 3 to the right is 7, and 9 up is negative 1. There's the sketch of our parabola. So the most important point is the vertex, and from there you just do this. Yep, from the vertex. We're going to see an example where the a value isn't 1, like it has like a 2 or a 3 or a half in front of here, and I'll show you how that works. But this is the basic idea.
I had no.
Okay.
Like I had no clue.
Yeah. Mm-hmm. Yeah, it's really not bad. But we spent very little time on it in class. It's been kind of a rush to the end, right? So that's understandable. And that's really what I want to spend some time on this week. All right, so 14.1.2 says graph this equation. So notice, it's got a minus 3 in front of it, right? So that means, and good Lord, I'll zoom in. So that means that this is going to grow 3 times as fast, and it's going to go down, right? This parabola is opening downward. Because of the negative, right? Yeah, it'll make everything go negative, right? So first, let's complete the square. And the way we're going to do this to get rid of that negative 3 is we can't divide everything because that'll make it nasty. Instead, what I'm going to do is I'm going to factor this out. So y equals, and I guess, I don't know, Evelyn likes this method. I think it's pretty good too. Let's just divide by negative 3 to everything. Let's just do that. Maybe it'll be easier for you to see it. It'll seem kind of silly once we get to the end, but it'll make this side look nice at least. So if we divide this by negative 3, we get 2x. And if we divide this by negative 3, we get 2/3. Negative 2/3, I should say. There we go. It's a minus sign. Sorry about that. Plus. Cool.
Wait, plus is it?
Should be minus 2/3. Divide everything by negative 3.
Oh, I remember it was negative 3.
Yep. I almost missed it too.
Oh, that's why that's a 2.
Mm-hmm. So while this is going to be kind of gross on the left side, we can just ignore this for now. And then we can complete the square. We need x plus 1 quantity squared, right? That'll get us our x squared. That'll get us our 2x. But it'll also get us 1 times 1. What's 1 times 1? We don't want that.
So then x, and our x 1, negative 1, and our y is going to be
Close. Our x will definitely be negative 1. But we still haven't gotten rid of this negative 3 over here, right? We need y on its own. So what we're going to do is we're going to multiply that negative 3 back over. which is why it seems kind of silly that we did it in the first place. That'll make that a plus 3, and that'll make that a plus 2. Yep, negative 3 times every term. No, oh, distribute into here?
Yeah.
First of all, no. Second of all, can't, because there's a square here. You can't distribute it into a square. You'd have to expand it first and then distribute. So, all in all of that becomes y equals negative 3 times the quantity of x plus 1 squared plus 5. So yes, x will still be negative 1, right? Our vertex will still be negative 1. Absolutely. Because when you plug in negative 1, that makes this as small as possible. Who cares if there's a times negative 3 there, right? If I plug in negative 1, I get 0. 0 squared is 0. 0 times negative 3 is still 0, right? That's as small as I can make it. So when I plug in negative 1, I get 0 here, and then I add 5 to it. So that's my y value, 5. So my vertex is at negative 1, 5. Now it also asks about an axis of symmetry. I'll show you that in a second. Let's just graph our vertex first. Negative 1, 5. So zoom out. Negative 1, 1, 2, 3, 4, 5. And this one's going to open downward, so I'm going to write my point up here. Because it's going to open down because of that negative. I'll zoom in. Yeah, exactly. Typically I am notorious for writing it in the way of my graph. So it's good to stop and think about where can I put this that's safe. All right, so a normal graph, Joseph. This guy, y equals x squared. We know how that works, right? If we plug in values for x, we can get values for y. Negative 3 becomes 9. Negative 2 becomes 4 when we square it. Negative 1 becomes 1. 0 is 1. 1 is 1. 2 is 4. 3 is 9. I'm just choosing random points. Like, it's nice to do negative 3 to 3. When you take pre-calculus, that's just what they do a lot of the time to get a good view of the graph, right? Here's some really common points. So I like doing negative 3 to 3.
Would that negative with a 0 be a 0?
Oh, definitely. Thank you. There we go. So that's how a regular graph works. But our graph grows 3 times faster, right? Here. 3 times faster, and it goes down. So instead of negative 3 getting 9, here's the graph we really have. Y equals negative 3x squared, right? All the rest just kind of tells you where it starts. This is how it grows. So our graph is going to look more like this when I plug in negative 3. Yes, I'm going to get negative 3 squared, which is 9, right? But then I'm going to times it by negative 3, and I'll get negative 27. See how that's growing 3 times faster and in the opposite direction? Right? Negative 3 will be negative 12, yep. Absolutely. 3 times faster in the opposite direction. So negative 1 normally gets 1, but we're going to go 3 times faster in the opposite direction, negative 3. 0 will still get 0. That doesn't shock anybody. 1 will get negative 3, 2 will get negative 12, and 3 will get negative 27. So it's just 3 times faster in the opposite direction. All this negative 6x and plus 2 stuff, that just tells you where it starts, basically, right? After we move things around. How it grows really just comes down to this, right? 3 times in the opposite direction. So normally, when we go 1 to the right, we go 1 up for our regular parabola, right? But now we're going to go 1 to the right, and we're actually going to go 3 down. Right? Over here, I can show that. Right? Negative 1, 3, 1, 3, negative 3. Is that making sense?
Are these like small boxes for like this?
Say it again.
Are they like the micro boxes for like
they're like fractions and stuff. You can make it whatever you want, but yeah, it's just fractions.
How do you demonstrate the 20?
So 27 we're probably not going to have room for, and that's totally fine.
So we're just doing next.
So I'm gonna, yeah, usually what I do is I go 1 to the right, and this one is going 3 times as fast, so 3 down. 1 to the left, 3 times as fast means 3 down. If I go 2 to the right, normally that gets me 4, right? 2 gets 4. But now 2 is going to get negative 12, right? 3 times in the opposite direction. So here's 3, 6, 9, 12. And it's symmetrical. And then after that, I'm running out of room. So I'll just make my quick sketch. There you go. Yeah, 2 gets you 12, right?
Oh, yeah.
Yeah, and 3 gets 27. So that's all we're doing. It's you find the vertex, and then you think, how is it going to grow? 3 times faster and in the opposite direction. So instead of 1 getting 1, 1 squared is 1, right? 1's going to get negative 3. Instead of 2 getting 4, it's going to go 3 times faster, opposite direction. 2's going to get negative 12, right? That's it. If it was a fraction, you just times it by a fraction, right? That's really all this is. So there you go. There's your graph. Now, it did say something about an axis of symmetry. It might even mention something like that in the last problem. I always forget about this. The axis of symmetry is this. So I'll use a black marker. Do you see how it's symmetrical here? Yeah, how it's symmetrical on either side, right? The symmetry. So they want to know, what's the equation of that line? Well, that's super simple. It's x equals negative 1. Yeah, I just drew my it was looking weird to me. Here's my axes. Yeah. Do you see how all the values on that dashed line are negative 1 something? Negative 1, 0, negative 1, 1, negative 1, 2, negative 1, 3, negative 1, 4, negative 1, 5, right? So really, it's whatever the x value of your vertex is. That's your axis of symmetry. Yeah, that's it. Just wants to know what's the equation of that line, which is a tough question because usually we're used to y equals mx plus b for equations of lines. These are the easiest lines, which means they have the weirdest equations. It's all the points where x is negative 1.
There's very few actually.
Yeah, exactly. Now, we're going to have other ones that tilt, right? We talked about that go sideways, and that's going to change things. That's going to have an axis of symmetry where it's y equals something, because all of those will have the same y value, the same height. These all have the same horizontalness. Something going this way would have the same verticality. They'd all be the same height, but different right and left.
Are imaginary numbers only 12 and 13?
Correct, yeah. I mean, we'll have a little bit of that in 14, but not much, because we're graphing. Graphing with imaginary numbers requires 3D.
We don't have.
I'm not, no, thank you. I'm not making you do that. So now we got circles, okay? Or sorry, not circles, no. We've got 2 parabolas. It says it wants you to graph y equals 2 times the quantity of x minus 4 squared minus 7. That's a parabola. Can you tell where the vertex is for this one? It's not negative 7, negative 7. What number do I plug in for x to make this as small as possible?
4.
And when I plug that in, everything zeroes out except the minus 7, right? So that's the vertex for this one, right? What about the vertex for this? This one's a little weird. Do you notice what's weird about this one? What's weird about it? It's not identical. There's something different. Not really. It'll just make it go downward. The big difference is x and y are switched. This is going to be a sideways one, right? So its vertex, what value do I plug in to make this as small as possible? Well, what can I plug in here to make this as small as possible? What number?
1.
Nope, 1 won't make it as small as possible. It's not a trick question. It's 4.
Oh, it is.
But I'm not plugging it in for x, am I? So 4 will be the y value that I plug in.
So the other base is
Kind of, yeah, kind of. That's an interesting idea. So when I plug in 4, that makes everything 0. And 0 minus 7 gets me negative 7, right? So what is x going to equal? Negative 7. Ah, that's kind of interesting, huh? Yeah, so these are special parabolas. They gave you ones that are almost identical. They're just rotated. And this one's going to open downward. And by downward, I mean to the left, because it opens right or left. And this one's going to open upward, right?
So you write down, you graph both.
Yeah, we're going to graph both of them. So it says find the vertex of each graph. Did it. How are they both related? We'll be able to talk about that once we see it, right? But I think we got the idea. This one's going to move to the left. This one's going to move up.
So they're going to open at this rate just
Bravo.
direction.
Bravo. Yep. So let's graph these vertices, because that is the plural of vertex. That might bleed through. It's really hard to see the axes on here. 4, negative 7. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7. And this one's opening up, so I'm going to put this underneath it. 4, negative 7. There we go, way down here. And then the other one is negative 7, 4. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4. It is super common for people to accidentally switch the negative 7 and the 4, right? Because when they're finding the vertex, they are like, oh, what number makes this small? 4, right? And so they're automatically writing 4 here like they did this last one. But we're not plugging in for X, we're plugging in for Y. That 4 has to be here, right? That's super common, though, for people to goof that.
Second one's entering down.
This one moves right to left because X is here, right? So it's going to move to the left, right? Whereas this one moves right up and down, so it's going to move up.
So where did you put your graph?
This is what I did.
To the right of it?
Yeah, that way when it moves to the left, it won't be a problem. So now, all we need to know is a regular graph, right? X squared, right? When we plug in 1, we get 1. We plug in 2, we get 4. We plug in 3, we get 9. But this one's going to move twice as fast. So when I plug in values for X, like negative 3, negative 2, negative 1, 0, 1, 2, and 3, a normal graph would get 0, 1, 4, and 9. Right? But this one's going to grow twice as fast because there's this 2 here. So instead of negative 3 squaring and becoming 9, it'll square and become 9 and then get doubled. 18, it grows twice as fast, right? Negative 2 squared is 4, but this is going to grow twice as fast, so we're going to get 8. Negative 1 squared is 1, but it's going to grow twice as fast, so we're going to get 2. 0 squared is 0, times it by 2, you still get 0, right? And of course it's symmetrical, so we get 2, 8, and 18 here. And you can see this opens up. See how all these y values are positive? So that's going to head upward. So from our red vertex, when we go 1 to the right, we normally go 1 up. 1 squared is 1, right? 1 squared gets you 1. But we're going to double that. 1 squared is going to get you 2 now. And it's going to be symmetrical.
Oh, to the left.
1 to the right and 2 up. This one's going up and down.
Okay, I think that was kind of.
Yeah, having color helps too. I know my red one goes up. So normally when you go 1 to the right, you get 1 squared and go 1 up, right? But we're going 1 to the right and getting 2, twice as much. 2 to the right would normally get 4. We're going to get 8. So 1, 2, 3, 4, 5. Oh, God, I lost track. 1, 2, 3, 4, 5, 6, 7, 8.
Over by 2, correct?
Yep, 2 to the right, we'll get 8 up. Normally it gets 4, but we're going to double that. Normally 3 to the right or the left would get us 9. Because 3 squared is 9. But we're going to do double that. It's going to be 18. So this was 8. 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. If you can fit it on the graph, I'd appreciate it if you did. Most pre-calc teachers will say, I need at least 7 points for your parabolas.
Like, not on each side.
Yeah, in total. So 3 on either side, plus the vertex. At least that's what mine did. And if you want to label those points, knock yourself out. I'm not gonna. Okay? So again, it's growing like a normal parabola. 1, 1, 2, 4, 3, 9, but it's going twice as fast. This one, we got to be careful about, okay? X and Y are switched. So when we do this, we're not plugging in numbers for X like we were here. We're plugging in numbers for Y, aren't we? Mm-hmm. So this is where I'm going to put my numbers that I'm plugging in. Does that make sense? Plug those in for Y, see what happens to X. Now, we don't care about all the details here. Our vertex already took care of that. All we care about is it's growing twice as fast. We will, yep. It's going twice as fast in the opposite direction. So think about it. if I plug in -3, when I square that I get 9, right? But I'm going to go twice as fast in the opposite direction. So it's going to be -18.
So is this going to be this as
Yep. It will, won't it? Right? We're timesing it by 2. X and Y are switched. And of course, we're going to get negative answers because it's -2, not +2. So -2, when we plug it in for Y, we square that, we get 4. But this is twice as fast in the opposite direction, so we get -8. -1 squared gets you 1. Times -2 is -2. 0 squared is 0. Then we times it by -2. Still 0. One squared is 1. That's what normally happens. But we're going to times that 1 that we get after we square it by -2 and get -2. 2 squared is 4. That's what normally happens. But after we square it, we have to times it by -2. So we're going to get -8. And you'll notice this is symmetrical, right? And then we get -18 because 9 would be what we normally get, but we're going to double it in the opposite direction. So from our vertex, we're going to do this. Now be careful. This means when I move 3 down, I go 18 to the left. Does that make sense? So if I go here, let's start with this one. This says 1 down, 2 to the left. Is that making sense? So 1 down, 2 to the left. This says 2 down, 8 to the left. So 2 down gets us 8. 1, 2, 3, 4, 5, 6, 7, 8. And that's looking like a sideways parabola. Now it should be symmetrical. Hi, welcome. Do you see how here it says 1 up? Because it's in the Y column. 1 up. Yep. So 1 up and 2 to the left. So we start here. 1 up and 2 to the left. Making sense? It should be symmetrical, and I'm going to show you that. 2 up, 8 to the left. 2 up, 8 to the left. That's here. So here's our blue parabola. Yeah, it's super easy to goof these up because they're so tricky to like conceptualize. But that's the idea. You got to watch out for X and Y switching. These are the numbers we're plugging in. 3 down, 8 to the left, or 18 to the left, right? So how are these related? Exact same parabola. One's just rotated to the left. Yeah, that's it. They're growing at the same rate. It just, this guy's cut off, right?
And then the vertex would just be whatever for the, we found the Y vertex for the one going sideways.
So do you remember in geometry where you did rotations?
Yeah.
This is a 90-degree rotation clockwise, or counterclockwise, I should say. So it's basically like the vertex is just coming along for the ride.
The vertex is.
Yeah, don't worry about it so much. Once you have them labeled, you're good.
So if the vertex, so for this, so for the right one, the vertex would be 4, right?
Oh, you're talking about axis of symmetry.
Oh, wait,
yeah, our axis of symmetry. So for this, I'll use pink. It's probably not going to show up very well. That wasn't too bad. So our axis of symmetry is all the points on this line have x equals 4. You see that? That's our axis of symmetry. Because we have 4, 0, 4, 1, 4, 2, 4, 3. Like literally sit down and kind of think about it, right? Now over here, our axis of symmetry is this way, right? It's a horizontal axis of symmetry, which means our parabola opens to the right and left. So the equation of this one, well, if you look, we have 0, 4, -1, 4, -2, 4, -3, 4. All the y values are 4. So the equation for that is just y equals 4. Welcome. My TV died.
That's fine.
Right before we started, so we're on this now.
Lightsaber joke. You're thinking Mr. Mac is gone.
Nope. I'm here. So that's for that. So I think what we're going to do is we're going to continue on with this one, and then we'll go back and hit the other ones for you. Does that make sense? Okay. So how are we feeling about this, Joseph? Better? Better is the word.
I'm doing pretty good.
Okay, okay. It's a little weird. It takes time, and we haven't had a lot of time for it.
Oh, yeah. I just finished the even call 2 pages away from I go for the previous one.
Yeah. So this next one is not a parabola. How can you tell?
It has more together.
x squared and y squared, right?
I remember you going.
It's a circle. You may have been gone or something. I can't remember.
I
I'm going to rearrange it like this. Put all my x's on the same spot, and then I'm going to do my y's. So we need to find the center of the circle, and we got to find the radius. Good news, that's super easy to do. You just got to complete the square. So let's complete the square over here. X minus 4 squared, yeah? Does that sound familiar? That x minus 4 squared is going to get us x squared. It's going to get us negative 8x, but it's also going to get us what? When we multiply this out, we get x times x, love it. Negative 4x, that's that. 16, which we do not want. Yep, that would change the problem if that popped up, right? So we got to take care of that. Over here, if we complete the square, plus, we need y plus what?
5.
Not 6.
No.
3, yep. Because if we get y times y, that's y squared. Y times 3 and another y times 3 gets us 6 y's. That's good. We're also going to get 3 times 3, which is 9, right? See how there's no plus 9 here? So if we minus 9, then I haven't changed the problem. When I rearrange this, I get x minus 4 quantity squared plus y plus 3 quantity squared equals, I'm going to add the 16 and 9 over. It's going to get me 36. And I should close this parenthesis. There we go. So this is the standard form of a circle. What it's telling us is that the distance between any point and this point will always be the root of 36. What's the root of 36? 6. So the radius is 6.
Wait, so from the point, every 6 there will be up 6, down 6.
From this point, 4, 3, essentially, right? And we'll talk about it in a second. All of the other points, that's what x and y are, right? All the other possible points will always have a distance of 6.
Now I remember this.
Right? So what's our center? Well, our center is the point that has 0 distance from this point, right? So what do I plug in to make this 0? 4 for x. And what do I plug in to make that 0? Minus 3 for y. That's the point when you plug it in, 4 and negative 3. You get 0, right? It's not on the circle. It doesn't work, right? It doesn't equal 36. It equals 0. It has 0 distance from itself. So our center is at 4, negative 3, and our radius is 6. So now we're going to graph that. We're going to look at this awful graph down here. There was a reason why I had all these tiny little dashes in there, and I think it was because, not so you could graph fractions, but because it showed up better on copying. But that might have been a school with a much worse copier. I think I need to get rid of them. So 4, negative 3 is 1, 2, 3, 4, 1, 2, 3. That's the center of our circle. 4, negative 3. And the radius is 6, right? So let's go up 6, right 6, down 6, and left 6 to get some more points. If I go up 6, I'm going to end up at 4, 3. 4 positive 3. If I go down 6, 1, 2, 3, 4, 5, 6, I'm going to end up at 4 what? Not 7. Go down 6.
Oh, no.
I'm at negative 3.
Oh, minus 10.
Nope, go down 6. I'm at negative 3, go down 6. 9, negative 9. It's okay. Pressure's on. And if you want to label these points, that's cool. If you don't want to, that's fine. I can just count them myself and make sure. I like labeling them because if I accidentally put it in the wrong spot, which a lot of people do, if I say the number, I can be like, oh, they meant the number, right? Yeah. Now, if I go right 6, 1, 2, 3, 4, 5, 6, I'm here now. So I'm no longer at 4, negative 3. I'm at 10, negative 3. I went 6 in the x direction, so that's a 10, right? I didn't move up or down, so the negative 3 doesn't change. And you can count that out if you want, 10, negative 3. If I go 6 to the left, using my radius, I'm no longer at 4, negative 3. I'm at negative 2, negative 3. You guys smell what I'm stepping in there? 6 to the left. Again, if you want to count it from the origin, you can. I'm just kind of lazy.
You want us to draw a circle?
Oh, yeah. This is the graph. That's how you sketch it. This is going to be the world's worst circle. Speaking of putting it in the wrong spot, 1, 2, 3, 4, 5. No, I did that. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Yeah, it just looks weird.
A circle looks like a square.
Yeah, mine's a squircle. Definitely. But there it is. There's the sketch of my graph. So what do? Back up and run over this again. We took all this crap and we arranged it so x's are together and y's are together. We completed the square, moved the extra crap over. The root of this will be the radius. Luckily, root 36 is a nice number. It's 6. And the center is whatever makes these guys 0. That's it. If you're feeling good about complete the square, this isn't that far-fetched, right? Graphing it, graph your center, go 6 in every direction.
Graphing this is really simple.
Yeah, easier than parabolas, right? How we better? Better? Any questions on this? Yeah, we probably need to hit the complete the square part, right? We did that with Joey. All right, so now we're on the intermediate questions. So do you want to take a look at these, or are we good for the night on this? The 1/3 here means it grows slowly, right? It's going to grow really wide and upward.
So it's basically the same as, but it's just going to be a lot slower.
Yes, and it's X and Y switch, so it's going to go to the right instead of up. Do you want to see it? There's not that much on this. We don't have to do all these intermediate questions. I think the graphing would be good.
What are all of these more every time there's word problems.
Yeah, there's a lot of word problems, which I'm not too worried about. Like I said, 14 is kind of just 2 sections. We go over graphing really briefly, and then the rest is kind of up to you. It's towards the end of the year. Understanding takes time, so you're going to be fuzzy on this. I'm pretty lenient on this stuff. I'm not looking for perfect. And of course, we already did all the basics, right? That's really what I want to get. It's just graphing circles and graphing parabolas. This one's a little weird. First of all, X and Y are switched, so it's going to open this way instead of up and down. Okay. To find this point, we got to get it in complete the square form. So here's what we're going to do. I am going to do this. I'm going to times everything by 3, and we're going to get 3x equals y squared plus 6y plus 3. I'm going to move that 3 back over later, but for now I'm going to get it out of my way so I can easily complete the square. Y plus what quantity squared? What do I need? X and Y are switched.
Oh, okay.
Yep, that's why it's opening to the right. Yeah, that's the other tricky thing about this one. So what do I need here? So that I end up with y squared plus 6y. Well, think about it. I'm going to get y times y squared. I'm going to get y times whatever that is, and another y times whatever that is. And they have to add together to 6. If I do 3, yep. Right? 3 y's and 3 y's will get me. Right? I'm going to get the same thing twice. But it also gets me a plus 9, which is not in the original problem. So I'll put a minus 9 so I don't change the problem. Now, before we get all excited, I need to get rid of this to be able to graph it. So I'm going to divide everything by 3, or if you want, times everything by 1/3. So I'm going to write that up here. X is going to equal 1/3 times y plus 3 squared. And then see how I have multiple terms over here? Negative 9 plus 3 is negative 6. Are we cool with that? That's negative 6. Minus 6. I divided this by 3, times it by 1/3. What's negative 6 divided by 3? Negative 6 divided by 3 is negative 2, right? It's okay. It's okay. It's the pre-algebra that kicks you guys' butt, right? So here's what we did. We times everything by 3 to get rid of the fraction. Then we completed the square, and then we divided everything by 3 to move it back, okay? Dividing by 3, same thing as a third. I don't know, some people like that better. And then negative 6 divided by 3 is negative 2. So here's where our vertex is, and this is going to be really weird for you because you weren't here for this. Joey's going to feel a little bit better. Our vertex is, what makes this as small as possible? What do I plug in for y? What makes all this small? Negative 3 will make this 0. That's as small as you can make it. So negative 3 is what we plug in for y. right? So I write -3 for my y-coordinate. That's for my vertex. That's this guy. When I plug in -3, I get 0 here. 0 squared is 0. 0 times 1/3 is 0. But then I'm -2 and I get -2, right? And that's what x will be when I plug in -3. So this is my vertex. I'm just asking what number makes this as small as possible? -3. After I plug that in, what happens? Everything goes away except -2. Because all this becomes 0. So now I'm going to graph that vertex. -2, -3. That's over here. -2, -3. And because x and y are switched, it's not going to open up or down. It's going to open right or left. Do you see how this value here is positive in front, 1/3? So it's going to open to the right. If that was a -1/3, it opened to the left. That's all. All right, so this is not the order you should be learning this in, but Joey, we're going to do this, okay? A normal graph that has an a value of 1 is like this guy, y = x squared, right? Here's how a normal graph works. Okay, this is just my little note on the side. I'm going to choose some numbers to plug in for x, like -3, -2, -1, 0, 1, 2, 3. If I were to plug these numbers into a regular parabola, the most basic parabola, this says square your x to get y, right? What happens when you square -3? What happens when you square -2? What happens when you square -1? What happens when you square 0? 0, yeah, that's a mistake I made earlier. And then 1 squared is 1 still, 2 squared is 4 still, 3 squared is 9 still. So that's a regular graph, right? It starts at the origin, 0, 0, -1, 1 is a coordinate, -2, 4, 3 to the left, 9 up, 1 to the right, 1 up, 2 to the right, 4 up, 3 to the right, 9 up. That's a regular parabola, right? Our parabola is not starting at the origin. It's starting here, okay? And not only that, its a value isn't 1. Ours is 1/3, isn't it? So I'm going to do that down here. Our parabola is going to be like this. Yes, it's got more stuff after it, but that stuff just tells you where you're starting, okay? Notice not only, ooh, hold on. Don't write down what I just did. Ours is actually this, isn't it? X = 1/3 y squared. Right, x and y are switched in this one.
So we're starting off with our y.
Uh-huh. So we're not plugging in values for x like we did for our last one, right? We were plugging in values for x and seeing what happens, right? Now we're plugging in values for y. And if you're clever, you can think of better values to plug in than these guys, but these are the tried and true ones. We're going to get some fractions. It'll be all right. So instead of plugging in for x, we're plugging in for y. We're still going to square it, though, right? See how it's going to square it and get 9? A third of it, right? It grows a third as fast. So I'll do that again in slow motion because she wasn't here for the first 10 we did, right? So -3, when we square it, gets us 9, right? 9 times a third, 9 times 1, 9, divided by 3, 3. So our graph is going to do this. -3 squared is 9, times a third is 3. If we plug in -2, yeah, we're going to square it. We're going to get 4, right? Just like we would normally. But we're going to get a third of 4. What's 4 times 1? 4. What's 4 divided by 3? 4/3. It's going to be a bummer. If you're clever, you can pick better numbers to plug in, but I don't want to stretch your brains too hard. We'll just go with these, and whatever happens, happens. It's a sketch after all. If I take -1 and I square it, that gets me 1 normally, right? That's good, and we'll still get 1, except we're going to times it by a third. We're going to get 1/3. I'll write that over to the side because I'm running out of room. 0, as you might guess, still gets 0, right? And these are symmetrical, yeah? 1/3, 4/3, and 3. Finally, a whole number, right? So what does this mean? This means if we start here and I go 1 down, do you see how this is a y value? If I go 1 down, I go a third to the right because that's an x value. So 1 down, 1/3 to the right. That's like here-ish. So I just did this one. 1 down and a third to the right. from my vertex. I'm going to pause there. We feeling okay about that? 1 down, because it's the y value, and a third to the right. You could have also done a third to the right and 1 down if you want to do the x value first. This says 2 down. So if we go 2 down, we're supposed to go 4 thirds to the right. So here's 4 thirds right here. 1 and 1/3, yeah? So I just did that one. And it can be helpful to cross these out as you go. Don't scribble them out because you might make a mistake. And then you have to go back and figure out what you wrote. This says if I go 3 down, finally a whole number, I go 3 to the right. So 3 down, 3 to the right. I like doing these individually instead of being like, oh, they're symmetrical, because I want to make sure I didn't goof. Right? Maybe I goofed up these 3. I start graphing these other ones and they end up going this way or something, right? 0, 0 means I go 0 down, I go 0 to the right. Okay, did that. That's just where I'm starting, right? Make sense? This says 1 up, 1/3 to the right. 1 up, 1/3 to the right. That's definitely symmetrical. 2 up, 4 thirds to the right. That's here. And 3 up, 3 to the right. That's here. So here's the sketch of my parabola. It's pretty wide compared to a normal one. Normal ones are pretty skinny, right? So that was a lot, but this is an intermediate question. We got a lot going on here. We got a sideways parabola. X and Y are switched. That's a pain. We have to actually deal with this 1/3 at the top here, right? That's a pain. That's another thing you got to juggle. We have to know how a basic graph works, right? And then we have to use that to figure out how our graph is going to work. Exact same thing, just we're switching X and Y and we're timesing by 1/3. It's going to grow slower. But it's a couple different things to juggle. On their own, not too tough. Altogether, it's a mild question, or a medium question, I should say. That's the last graphing one, I think. That's in the intermediate, at least. Yeah, no, just period. Okay? So I think that's worst case scenario that you guys should be worried about at all. We cool with that? All right. So Joseph, would you like to see some more examples for this stuff so you can get more comfortable? Should we go back to the beginning and hit some of these more basic ones for you? Would that be helpful?
Yeah.
Okay.
First, I think I'm good.
Yeah, you think so? Like straight across the board? Head on out, man, if you're feeling good. What I'll do is I'll go grab another 6, right? And we'll just do the beginning ones. Yeah, of course.
Mr. Mack,
Yeah.
I don't recall grabbing a 6 while I was here.
Oh, for real?
Yeah.
Oh my god, I'm so sorry.
It's okay.
I'm so sorry.
Like, I looked through, I
You
need
were
to double
sitting
check my
there
marker, I'm like,
this entire time just like, okay, I'll just take notes.
well, I just sat on scratch paper. So.
Wow, how nice of you. Totally fine to interrupt me. Totally fine. I'm here for you guys. All right, so we're going to go to the beginning, and this is going to feel way easier compared to what we just did. Okay? So it wants us to graph this. This is a parabola, and this thing is in focus. It's just not in focus up there. Okay, cool. All right, so can you sort of read that?
Yeah.
X squared minus 8, x plus 6. Cool. All right, we're going to make this work. On TV, it's fantastic. It's just this thing's a piece of junk. All right, so I don't know. I know this opens up and down because y is here and x is there, right? Okay? And it's going to open up because it's a positive a value. And it's going to grow like a normal parabola, y equals x squared, okay? Its vertex is going to be in a weird spot. And I don't know where that is. I can't tell from this how to make this as small as possible. It's weird, right? Because I could plug in some negative numbers and I could actually get some negatives here and, right, it's hard to tell. But if I complete the square, it's super easy. So I'm going to get x, and if I take half of this guy, I've got my perfect square. Inside of here, I've got x times x, x squared. Inside of here, I get a negative 4x and another negative 4x for a total of negative 8x's. But I also get negative 4 times negative 4, which is going to be positive 16. And that's not in the original. No, it's okay. So if I minus that 16 and add the 6 that was on at the end, this is the exact same equation I started with. It's just a different way of looking at it. Okay? So if I simplify this, I get this. And it's really easy to tell what the vertex is. So my vertex, its coordinate, what do I plug in to make this part as small as possible? What do I plug in for x?
Big questions.
Well, think about it. We have a square, right?
Okay.
If I'm using regular numbers and I square something, what's the smallest number I can get? Well, if I plug in 1, I get 1. 2 gets 4. 3 gets 9. I'm heading in the wrong direction. If I plug in 0, I get 0. That's pretty good, right? If I plug in -1, I get 1. So that's bad, right? 0 is as small as you can make a square. So how do I make this 0? What do I plug in to make this 0?
Oh, positive.
Positive 4.
Okay.
That's the best number to plug in. I knew you were overthinking, but it was important to go through that process. So 4 makes this whole thing 0, and that's the smallest you can get when you square, right? So I get 0 when I plug in 4, but then I have to minus 10. What's 0 minus 10? -10. So that's what y will equal when x is 4. When I plug in 4 for x, I get -10 for y. That's why this complete the square form, or vertex form, is super easy to find the vertex. So we know our vertex is at 4, -10. So let's graph that. 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we know it's opening up. In a normal graph, y equals x squared. We know how this works. I'm going to make the chart, but we know how this works. When we plug in numbers for x, we square them and we get y. So a normal graph would get us 9, 4, 1, 0, 1, 4, 9, right? Now, how similar is this to a normal graph? Well, it's got a different vertex. It doesn't start at 0, 0, right? It's got this weird stuff that's going to screw things up. But its a value is the same. Do you see how they both have a 1 in front of the x squared? Right? I mean, you sort of see that. It's pretty blurry. So that means it grows the same way and in the same direction. So this is super easy. We don't have to change anything here. We don't have to make a second chart. 0, 0 we did. That's starting here, going 0 up, 0 over. This says if we go 1 to the right, or sorry, 1 to the left, we go 1 up. 1 to the left is 1 up. If we go 2 to the left, we go 4 up, right? Because 2 squared is 4. If we go 3 to the left, we go 9 up. Because 3 squared is 9. So notice this one, we just take these numbers and we just go with it. We don't have to make a separate chart, times it by 2, negate it or anything. And of course it's symmetrical, right? If we go 1 to the right, 1 up. 2 to the right, 4 up. And 3 to the right, 9 up. And there's our parabola. It's the exact same thing as the most basic parabola. It just started in a different spot. It didn't start at the origin.
Okay, that wasn't horrible.
It isn't. It isn't. It's not going to feel great because it takes time. But like, if you did this for a week, you'd probably be okay, right? So what do we do? We completed the square carefully, right? Then we knew 4 and -10 would be our vertex. And because this is a regular one...
Can you point me towards the library?
Yeah, library's down that way. Keep walking. It's on your left by the vending machine. So anyway, 4 and -10, if we plug those in, that's our vertex, right? And because the a value is 1, it grows the same as this guy. Oh, sorry, you can't see that. It grows the exact same as this guy would. We know how this guy works, right? Pretty easy. So we do the same thing. 1 to the right, 1 up. 2 to the right, 4 up. 3 to the right, 9 up. And we make it symmetrical.
And that's all you have to do.
That's it. That's it. I'm literally, because like this is like really bare bones, because the book isn't like, here's 20 examples of the same thing, which is good because it doesn't waste your time. It's also bad because you want more practice. I'm going to run through, and you can write notes if you want, but I think watching would be best. I'm going to make up another one. I'm going to do the exact same thing, okay? So let's do this, and I'll zoom out a lot so I know that you can see everything. Y equals, let's do x squared minus 10x plus 1. Okay? To graph this, I need vertex form. Right? Complete the square. But I'm also going to get a plus 25 from this. I don't want that. So far, so good? Okay. So really, this equation is the same thing as this. These are exactly the same. And I can graph this. My vertex, what do I plug in to make this as small as possible?
Positive 5.
+5 for x, so I'll put that in the x spot. If x and y were switched, I put the 5 in the y spot, okay? And then when I plug in 5, I get 0. 0 squared is 0. 0 minus 24. Negative 24, that's what I get for y. So I'm going to graph that. That's actually a pretty low number, but here. Here's 5. 1, 2, 3, 4, 5, negative 24. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Way down there. Almost didn't have room. And it's going to open up because a is 1. And it's going to grow like a normal parabola. This is the normal parabola. We know how this works. Eventually, you're going to get tired of this chart. You'll just do it in your head. Right, 9, 4, 1, 0, 1, 4, 3. So using this, starting at our vertex, 0, 0, we already did it. Start there. Don't do anything new. 1 to the right, 1 up. 2 to the right, 4 up. That's 1, 2, 3, 4. 3 to the right, 1, 2, 3, and 3 up. Or sorry, not 3 up. 9. Right, 3 squared is 9. 1, 2, 3, there's 4, 5, 6, 7, 8, 9. And it's symmetrical. 1 to the left would be 1 up. 2 to the left would still be 4 up. 3 to the left would still be 9 up. There's my parabola.
What's the problem that you just did with Joey's like different than this because you had to use a different chart?
When you have a number in front of this x squared, like a third or negative 2, then you have to times everything by negative 2 or everything by a third. Yeah. And it changes how quickly it grows, right? Or what direction. That's it. And we can go back and do one of those. How do you feel about that?
That it seems simple, like beyond.
It takes time. It just takes time.
I stressed about this for so long.
Yeah, that makes sense. It's going to take some time, but you've got time. It is Tuesday? Wednesday?
Tuesday.
Oh my God, it's only
Tomorrow's
Tuesday?
Wednesday.
That's awesome. You got Wednesday, you got Thursday, and your final is Friday or is it Monday or Tuesday?
I don't know for classes. I have it like.
Gotcha. I think it might be Tuesday. I don't know. Don't quote me on that. I don't want to get too excited. We still have plenty of time, even if it's Friday, right? Mm-hmm. So you'll have time to digest this, and you can always get some more examples from the book, or I can print you another quizish that has numbers, or you can just make up numbers on your own, kind of like I did, right? Mm-hmm. Just be careful about getting giant numbers and graphing it, but you know. Cool. All right, let's do this one. Now, this one is an example of what you wanted to talk about, right? It has a number in front of the x squared. It's negative 3, and it's super blurry. Focus. Better, okay. The graph looks awful, but at least you can read that. All right, so for this one, here's how we're going to handle this. When I complete the square, I don't want that negative 3 there. So I'm going to divide everything by negative 3. It's going to look super gross for a second over here, but we're just going to ignore that, okay? If I divide negative 6 by negative 3, I get positive 2x. And if I divide 2 by negative 3, I get negative 2/3, which isn't as big of a deal as it looks. So again, what did I do? I divided everything by negative 3. It doesn't get rid of it because it has to go to divide every term, right? Mm-hmm. It's just going to hang out over there for now. So then I complete the square. I need x plus 1 quantity squared, because that'll get me the 2x I need. Unfortunately, not only does this get us x squared, which we love, 1x and another 1x, which we love, because that's 2x's, but it gets us 1 times 1, which is 1, and there is not a 1 up here. So now these are the exact same problem, just a different way of looking at it. And what I'm going to do before I simplify these is I'm going to times that negative 3 back over. I'm going to times this first term by negative 3. I'm going to times this thing by negative 3. Do not distribute. There's a square here. You can't distribute into that. And I'm going to times each of these terms by negative 3. When I do that, 3's divide out here. That's why I did it. I get y equals negative 3 times x plus 1 quantity squared. See, I'm just leaving that negative 3 out there. I can't distribute it, so I'm just going to leave it there. Totally fine. Negative 3 times negative 1, positive 3. Here, the negative 3's divide out, right? See how it says divide by negative 3? So that's gone. I just get plus 2. So my final form is this. Y equals -3 times the quantity of x plus 1 squared plus 5. That is vertex form. So it's a little annoying to have that -3 in the front, right? You got to divide it out, and then you got to throw it back on. You got to not distribute, even though it's really tempting, right? Because that doesn't work. You have to first distribute that out, x plus 1, right? And then you can times everything by -3, and we don't want to do that. We like this form because it's easy to tell what the vertex is. What number do I plug in for x to make this 0? Yep. And that -3 doesn't matter. When I plug in -1, I get 0 squared, which is 0. And 0 times -3 is 0. So I get 0 plus 5. What's 0 plus 5? So y value will be 5. There's my vertex. So still super easy to find the vertex. -1, 5 is here. 1, and then 5 up. 1, 2, 3, 4, 5. Now, danger, warning, danger. This one does not open up. Do you see how it has a -3 in front of the x squared, right? It opens down. And it's going to go 3 times faster than a normal one will. Just a reminder. A normal parabola has an a value of 1. And it opens like this. 3, 9, well, -3, 9, -2, 4, -1, 1, 0, 1, 1, 1, 2, 4, 3, 9. Ours is going to open 3 times faster and down. So how is that going to change things? Well, I'll show you. I'll make a little chart. Why did I do y on this side? I'm going to plug in the same numbers for x. -3, -2, -1, 0, 1, 2, and 3. And some of these numbers are going to come out huge. But again, we're not going to worry about trying to find good numbers to plug in. We're just going to go with these, and whatever happens, happens. So think about ours. Ours is basically this. Y equals -3x squared. That's basically what our graph is, right? Yeah, it's got all this other junk, right? All this other junk. But that just tells you where it starts. Really, it just boils down to this. So it's going to be 3 squared, -3 squared is 9, right? But it's going to go 3 times faster in the opposite direction. So what's 9? When we plug this in, we get 9. What's 9 times -3? -27. Do you see how it used to be 9? But it's 3 times faster in the opposite direction. 3 times faster in the opposite direction.
Is there like a pattern here?
Oh, for sure.
Oh, yeah.
Oh, for sure.
I see where yeah.
So normally, -2 gets us 4, right? We square it, we get 4. But it's going to go 3 times faster in the opposite direction. That's -12. See how this is 3 times faster and in the opposite direction of 4? Right, normally we plug in -2, we get 4. But we're going to times it by -3 when we're done. When we plug in -1, we normally get 1, right? Because -1 is 1 when you square it. But then we're going to times it by -3. And we're going to get -3. 3 times faster and in the opposite direction. Oh, I did 0 is 1. I keep doing that today. Up here, 0 is 0. 0 squared is 0, not 1. So 0 normally gets 0, right? If you plug 0 in, you get 0 squared. That's 0. What's 0 times -3? Still 0, right? For our parabola, we plug in 1, we get 1. 1 squared is 1, right? But it's going 3 times faster in the opposite direction. Do you see how it's going to be symmetrical? 2 squared is 4. Times it by -3, we get -12. 3 squared is 9. Times it by -3, we get -27. So all this is saying is, from wherever your origin is, don't do anything. Awesome. Already got it. From wherever your origin is, go 1 to the right, because that's an x value. Go 1 to the right and 3 down. 1 to the right and 3 down. Did it. Go 2 to the right and 12 down. Like I said, these numbers are going to get huge. 2 to the right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Way down there. Then it says if you go 3 to the right, go down 27, but we're not going to have room for that. So who cares? This says go 1 to the left, go 3 down. Oh my God, it's symmetrical. Who could have predicted? -2, -12, right? 2 to the left, 12 down. And of course, 3 to the left and 27 down ain't gonna fit. So we're just gonna keep on trucking like this. And there's our sketch. Okay, so this is a basic question because it requires basic understanding, but it's definitely a more complicated basic question than the last one. First off, we got to know what to do with that -3 in front of here. Divide it out, save it for later. Then we got to do the complete square like we do normally, but then we got to put that -3 back. When we do that, we got this. Vertex is -1x and 5 for y. After we graph that, then we think a regular parabola does this. 3 gets 9, 2 gets 4, 1 gets 1, 0 gets 0, right? Ours is going to be just times -3. So 3 is not going to get 9, 3 is going to get -27. 2 is not going to get 4, 2 is going to get -12. 3 times faster in the opposite direction. How are we feeling?
Very good. So basically, when
That's
you
incredible.
divide everything by
Yeah, sorry.
when you divide everything by -3 and then basically simplify it and then times everything by -3, that's not going to change.
I'm just moving it back, yeah. I pushed it over there, so I don't have to worry about it when I do this. And then I'm pushing it back. That's it. Yeah. Totally fine as long as you do it to every term. It's weird, but yeah. It's like adding 5 and then later subtracting 5. It's fine. As long as you did it to everything, you'll get back to where you started. So that's that. Now, this one is a bit of a pain. Okay? So this is like, this shouldn't be a basic question, honestly. It's having us graph 2 different parabolas. The reason it's basic is because you need to have a basic understanding of how this works in order to do bigger and better things. So this is saying, look, I've got a parabola. They already completed the square for us. Do you see this?
Yeah.
So let's have this be red. What's the vertex for this red parabola? Because we're going to graph it. What do I plug in for x to make this as small as possible? To make make it 0. You plug in 4. When you plug in 4, everything goes away except the -7. So that's what y will equal when you plug in 4. So we already found its vertex. That was easy. I'm going to graph that. 4, -7. And this is a regular parabola, right? It's y equals, and has a 2 in front. So it's definitely going to open up, right? It's got a 2 in front, y equals. It's just going to grow twice as fast as a normal one. So I'm going to write underneath here 4, -7, because it's going to go up from there. I'm notorious for writing this in the way of where I'm graphing. So I try and pause and think about where it should go. All right, this one's a little bit different, though. I'm going to highlight this one in blue. What do you notice that's different about this one? There are 2 things. Oh, you can't see it. Now you can.
It's y.
Yeah, in the
It's
middle.
negative.
Yeah. So first off,
Oh, so it's basically the same thing, but -2.
yes. X and Y have also been switched, though. Look.
Yeah.
So now our options, if x equals, it's either going to the right or the left. But it's -2, so we're going to go to the right or the left? It's going to go to the left. So it's growing twice as fast as a normal parabola, but it's going to go to the left. That's going to be a little annoying and a little confusing to graph, so hang on to your butt. However, we can find the vertex super easily. What number do I plug in to make this as small as possible? Now careful, caution, danger, warning. Nope, hold on. You're good, you're good. See how we plugged in 4 for x to make this 0? So I put a 4 in the x spot. I'm not plugging in 4 for x, am I? I'm plugging in 4 for y. So I'm going to put it in the y spot.
Oh.
Yep. This literally is like the #1 little mistake that people make. And then it screws everybody up and their graph looks awful. And they're like, what is happening? Mr. Mack, I'm having like a panic attack. And it's like, you literally just, y is what you're plugging in, right?
Just flipping it.
Yep. So we plug in 4 for y, everything goes away, right? And we get -7 for x. So yeah, these are flipped. And that's because they want to show you something, right? Not all graphs have to work that way. It's just these 2 they wanted you to graph. They're like, oh, let's have them be the same, except we'll change a few things. So yeah, just be careful where you put that 4. In this case, it goes in the y spot. So -7 for x, 1, 2. 3, 4, 5, 6, 7, and 4 for y. Oh, whoops, that's 3.
Into the left.
It's going to open to the left, so I'm going to write negative 7, 4 on the right side of this dot. And I definitely put an extra dot there on accident. Ignore that dot. Okay, so now we need to think about how these grow. Maybe we can skip the chart altogether. A normal one. When I plug in 1, I get 1 squared, which is 1, right? Go to the right 1, go up 1. If I plug in 2, 2 gets 4. You with me on that? 3 gets 9, but this one's going to get double that. So if I go 1 up, or 1 to the right, I'm not going to go 1 up. I'm going to go 2 up, and it's going to be symmetrical. Normally I go 2 to the right, I go 4 up, right? 2 squared is 4. But now I'm going to go 2 to the right and get double that. I'm going to get 8, aren't I? That puts me like here, and it'll be symmetrical. A normal parabola. When you go 3 to the right from its vertex, you go 9 up, because 3 squared is 9. But we're going to go twice as far. So we're going to go to 18. That's going to be a nightmare. 3 to the right. Here's 8. 18. Somewhere up here. There we go. So I skipped the chart altogether, and I just thought about it in my head. Actually makes it a little bit easier, doesn't it? If you want to label those dots, go ahead. I'm not going to. I'm pretty confident I got them in the right spot. I don't need the writing to save me. So yeah, normal parabola, 1, 1, 2, 4, 3, 9. This one, 1, 2, 2, 8, 3, 18. Make sense? Cool. All right, saving some brain power by not writing things down. Love that. This one's going to be a little bit weird though, okay? It's going to double it. Sorry. It's going to double it and make it negative. So instead of 1, 1, we're going to get 1, negative 2. You with me on that? 2, 4 is going to turn into 2, negative 8. And 3, 9 is going to turn into 3, negative 18. But pause. We're going to the left. Okay? So if I go 1 up, I'm going to go negative 2 to the left. And it's going to be symmetrical like that. Does that make sense?
Okay, so
Like literally turn the page if you need to.
Okay,
1,
up.
2. That makes sense? We're going to the left. This is where things get weird.
Yeah.
You just got to wrap your mind around it. So we're going to the left. So 1 up will get me 2 to the left. 2 up will get me 8 to the left. And it will be symmetrical. And I've run out of room. Yeah, you just got to stop and think and wrap your brain around the foot, as Michael Scott says in The Office. It's weird, but that's the idea. Do you see how it's the same thing as the red one, just turned to the side? Yep, that's it. So it's going to the left because it's negative, and it's going twice as fast. So we're heading to the left. 1, 1, 1, negative 2. 2, 4, 2, negative 8. That's the idea. This is like ultra crazy spicy for a basic question. And it wants to know how are they related. It's the same thing, but you turned it 90 degrees counterclockwise or something, right? However you want to say it, right? It's the exact same thing, it just rotated to the left. I don't care. I'm not big on that question. Kind of harkens back to geometry. You remember that, rotations? Did you guys talk about that in geometry? Rotating things? Probably, yeah. I'm not worried about it. So, how do we feel about, here's the vertex. It's 4, negative 7, and it's going up twice as fast. Love this one, right? Love this one. This one, the y value is 4, the x value is negative 7, and it's going to the left twice as fast. If you don't think about it too much, it's not terrible, but just be careful.
Yeah, I would just have to catch myself on
Yeah.
that, but I would figure that out.
Yep, yeah. All right, there's one more basic I want to do, and then we'll stop with this stuff. And it's graphing circles. Good news, graphing circle, really easy. In fact, you saw part of this, right?
Yeah, a little bit.
So here's how you graph circles. I know this is a circle because both of them are squared. It's a circle. I'm going to rearrange this. I'm going to write x squared minus 8x. I'll get my x's next to each other. Plus y squared plus 6y. And I'll have it equal 11. I'm just rearranging the order, okay? We cool with that? Do I know where the center is? Nope, but guess what I'm going to do? I'm going to complete the square. Are you okay?
Yeah.
Oh, you're just marking things down. Got it,
Yeah.
got it. I don't want to rush ahead. I'm here for you.
Nope, I'm on board.
That -4 blowing your mind? Or are you seeing where it's coming from?
The -8.
Yep, it's half of it,
Yep.
right? That's what we need.
Mm-hmm.
And then, of course, this is going to give us x squared. It's going to give us -8x, but it's also going to give us plus 16, which we don't want, because that would be different from the original problem. So I'll put a -16 next to it. So again, I just completed the square here, okay?
Did you do the same for the other?
Yeah. So I'm going to do plus whatever y in a square is. What number do I need next to the y?
Didn't we just do this one with Joey?
We did. It's okay. Stop.
Isn't it
Don't panic.
2?
It's not 2, but you said 2 last time too. 2. I'll get 2 y's and another 2y. That'll be 4 y's. That's not enough.
It's half. It's 3.
Yep, it's 3. Right, because we're going to get the same thing twice. It's okay. Don't freak out.
Struggle bus.
It's the pre-algebra that kicks everybody's butt, including my own. Variables, totally fine. Shouldn't be, but I am. Numbers, no. No, please no. So we're going to get y squared out of this. We're going to get 3y and another 3y to get 6y. We're also going to get 3 times 3, which is 9, and there was not a 9 in the original problem. So we have to put a -9, otherwise we're talking about a different problem altogether. Now I'm going to clean this up a little bit, and I'm going to write it all in perps. X minus 4 quantity squared plus y plus 3 quantity squared equals 36. And where did I get 36 from? I added the 16 and the 9 over. One thing you got to know is that this is Pythagorean theorem. A squared plus b squared equals c squared. C is the radius. This is c squared. So our radius is the root of that, which in this case is 6. Hooray for a nice root. Our center, just like when it comes to the vertex, is the most important point on a circle, although it's not really on the circle, is it? It's in the center of it. The question is, how do I make these 0? What do I plug in to make this part 0? Yeah, I put in 4 for x, right? And I put in -3 for y. So there's your center. Graphing circles easy. So we go to 4, -3 on our graph. 1, 2, 3, 4, 1, 2, 3 below. Barely fits on the screen there. I'm going to mark that 4, -3, just so I can see where it is. And then to sketch a circle, you just go from the center, whatever the radius is, right? So we're going to go 6 up, 6 to the right, 6 over, etc., right? So 6 up, 1, 2, 3, 4, 5, 6, place a dot. 6 to the right, 1, 2, 3, 4, 5, 6, place a dot. Down 6, 1, 2, 3, 4, 5, 6, place a dot. And left 6. And then we draw a beautiful circle, which I will never, ever be able to do when I sketch it like this. Pretty squirkly. Ta-da, it's a circle. So yeah, how do you make a circle? You find the center. How do you find the center? You complete the square. After you got that, you can even see your radius after you move everything over, right? It's 6. So you graph that and go 6 in every direction. If you want to label your points, you can. 6 to the right means this is now 10, -3. 6 to the left means this is -2, -3. Because all I'm affecting is the x value if I go left and right. If I go 6 up, I'm not affecting the y or the x value, I'm affecting the y value. So 6 up from -3 is +3. 6 down from -3 is -9. Or you could just, count them out if you want. But there's the graph of my circle. Every point on this circle, if you were to find its coordinate and plug it in, you do the math and you get 36. That's what a circle is. So there you go. That's all of the basics for this chapter, which are the hardest ones because we've spent so little time on it. How do you feel? Okay? Better?
Yeah, I mean, just for basics, this is fine.
Good. I'm glad you feel that way because fine is like, wow, you're doing great. Yeah. If you're like, I feel okay, I'd be like, that's normal. But if you say fine, wow, okay, yeah, you're really going to be okay. So yeah, that's the idea for this. Do you want to take a break? Do you want to go back and look at stuff? Do you want to take a break and go back and look at stuff? What do you want to do?
I know there's stuff I need to get.
Yep.
Or look at on
Okay.
these sheets, so let me do that real quick.
Yeah, take your time. Take your time. In fact, I'll use the bathroom, and I'll come on back. Do not destroy this rig. I'm gonna trip over these wires. It's gonna be awful. TV.
Not really. Okay, so probably okay. Where is my Oh, that's
And again, take your time if you need more time. No big deal.
I'm just circling questions.
Yep. And that's why we're here. So this thing isn't goofy. That's a little bit better.
Alright, I think I'm just gonna go for the number 4 closure.
Got it.
I went to the dentist, so if I'm talking something
Oh, okay.
Yeah.
You're fine. You're fine.
Okay, so
What do you want to start with?
11.4.1.
M41.
B.
Part B. Okay, cool. Let me grab a fresh one because this is one Joey and I were using. Because he had the exact same questions. Everybody has similar questions every year when we do the review. If it's not, I want to see all of them. It's the ones you guys are asking about right now. All right, so 11.4.1, rationalize denominators. So that means denominator means the bottom of a fraction. Rationalize means make it not an irrational number. So that's an irrational number, root 3. It's like 1 and change. But it goes on forever with no pattern. Not a nice number. Some people say that it is easier to think about these numbers when they're in the top of a fraction than the bottom. I think it's pretty irrelevant either way, but that's why we're doing this. We are simplifying the fraction. We're going to get this one done as well, part B, right? I want to show you this real quick, but part B, and you're going to go like, oh my God, that doesn't look simpler. And I agree with you. It definitely doesn't look simpler. So here's the basic idea. If I times by root 3 over root 3, I'm not changing the problem. And what I get is 5 root 3 over the root of 9. And that's why root 3 was a great choice, because root 9 is just 3. Root 9 is a nice root. This is asking what number times itself twice, because it's a square root, gets me 9. 3, right? So there's my answer. Doesn't have a root in the bottom. It's easier to work. I don't know. This is where things get weird. And I'm not going to do B right away. I'm going to show you a different example, because B is kind of nasty. So here's my example. What if I have 1 over the cube root of 4? Now the cube root of 4, oh God. The cube root of 4 is not a nice number. It's not. This is asking what times itself 3 times gets you 4. Well, 2 times 2 times 2 is 8. So 2 isn't it. 1 times 1 times 1 is 1. So it's between 1 and 2, right? It's not a nice number. But here's the downfall. A lot of people think I'm going to just times top and bottom by the cube root of 4, just like we did in the last one, right? But because it's a cube root, it won't work. What you get on top is the cube root of 4 times 1, which is this. Who cares about the top? The real point is this. We get the cube root of 16. And the cube root of 16 isn't a nice number, right? 2 times 2 times 2 gets 8, so that's too small. 3 times 3 times 3 is 27, that's too big, so it's between 2 and 3. This is still an irrational number. Doesn't work. So what are we to do? Here's what we're going to do. We're going to times by the cube root of 4 squared. And I know 4 squared is 16, but I think it's easier to see it this way. Now, when I multiply, the top happens. Who cares about the top? This is 4 times 4 times 4, also known as 4 cubed, right? Does that make sense? 4 times 4 times 4, 4 cubed. Earlier I did 4 times 4, which is 4 squared, also known as 16, right?
So, wait, hold on. Hold on. Okay.
Are the gears clicking? And what number do you times?
I'm trying to comprehend it. It's just not.
Oh, do you want me to pause?
Yeah, hold on.
Okay, I'll let you think.
So the cube root of 4 to the second.
Yeah.
So
here's
the inside of the root, is it 16?
Yep, that is the exact same thing as this. But I'm writing it like this. Oops, sorry. I'm writing it like that because I think it'll be easier to see in a second. Okay?
Okay.
If you wanted to, you could do this, and if you times those together, you would get the cube root of 64, which is a nice number. It's 4. 4 times 4 times 4 gets you 64. Okay? So here's why I'm using squares and cubes and stuff. Because 4 times 4 times 4 is 4 cubed, yes? And this is asking what times itself 3 times gets you 4 cubed. What do you times by itself 3 times to get 4 cubed? 4. Cube roots and cubes cancel. So what I need here, if I'm dealing with cube roots, is I need a cube inside of it. Does that make sense? A cube number. So that cubes and cube roots go away. I know, it's weird. It's weird. So, and the issue is, it's pre-algebra. And this is the part of the pre-algebra review and algebra 1 that everybody hates. So let me just refresh you on something, okay? The cube root of 8 is 2, because this is asking what times itself 3 times gets you 8. Cube root's 2, okay? Cube root is 2. So what we need is a cube number in here, not a square like 4 or 25 or 36 or 49. What we need is a cube number, okay? And the way to get a cube number guaranteed is to take a number and cube it, right? So as long as I get a cube number inside of a cube root, cubes and cube roots cancel, and you just get 2. So, for instance, what is the cube root of 5 cubed? 5 cubed is 5 times 5 times 5, 125, right? What do you times by itself 3 times to get 5 cubed? 5.
The root. I don't want to memorize it as just, if there's a 3 in the root and there's the root.
Yeah, I know what you mean. Yep. No, and I appreciate that. So here's what we're doing, right? That's 125. And we're asking what times itself 3 times gets you 125. That's 25.
Oh, okay.
That's 125. But you might notice a pattern, right? There's 3 of them. So if I think of this question like this, the answer becomes obvious. 125 is just 5 cubed. What do you times by itself 3 times to get 5 cubed? Well, you take 5 times itself 3 times to get 5 cubed, don't you? That will get you 5 cubed. So this is the cube root of 5 cubed. That's the cube root of 5 cubed. Again, this is the thing that's kicking everybody's butt. It's the pre-algebra. So what if I have the 4th root of something, like the 4th root of 2? Not a nice number. What do you times by itself 4 times to get 2? 1 and change, right? So if this is my problem, and I times by this, top and bottom, it's up there too, okay? I'll get the 4th root of 2 cubed times 2. So 2 times 2 times 2 times another 2. Isn't that 4 2's being multiplied?
Yeah.
What's the 4th root of 2 to the 4th? It's 2. What number do you times by itself 4 times to get this? Well, 2, right? It kind of tells you the answer, doesn't it, right? 2 times itself 4 times will get you this. So this becomes 2 in the bottom. So how did I know I needed a 3 here? Well, I've already got 1 2 here. If I have a total of 4 2's, ta-da! Cube root of 4, or 4th root of 4 is 4. 4th root of 2 to the 4th is 2. There we go. Do another example. So it sinks in. Again, it's the pre-algebra that's kicking our butt. If I have the 5th root of 3, that's not a nice number. So 1 over the 5th root of 3. 1 over the 5th root of 3. If I times it by 3 to the 4th, inside the 5th root, top and bottom, I end up with the 5th root of 3 times itself 4 times itself another time, that's 3 to the 5th. And what does that become? Just 3. Another example. This one's slightly different, okay? Slightly different. If I have 1 over the 5th root of 3 squared. Okay, 3 squared is 9, right? But I'm going to think of it as 3 squared. I need to multiply by, top and bottom, the 5th root of 3 cubed. So that I'll end up with the 5th root of 3 times 2. 3 times itself twice. 3 times itself 3 times. How many 3's am I multiplying here? 5 of them. Do you see 2 and 3? 5 of them?
It's kind of like it.
Yeah, exactly, right? This is 3 times 3. That's 3 squared. And we're timesing it by 3 times 3 times 3. Looks like 3 to the 5th to me. Right? 3 to the 5th. 3 to the 5th. So that's what we get in the inside. And it's nice to think of it this way, because I don't know what 3 to the 5th is up top of my head, right? But I know this cancels out and I get 3.
Okay.
So now on to your problem. Your problem is this. 1 over the 9th root of 2. And everybody likes to just multiply by itself, right? But that won't work. Here's what everybody likes to do, and I'm going to show you why it doesn't work. Yes, we get the 9th root of 2 on top, because 1 times that is itself. We get 9th root of 2 squared. Or 2 to the 4th, right? Do you see how this does not work? The 9th root of 4 is still an awful number. What do you times by itself 9 times to get 4? Nothing nice, right? So this is still stuck. However, if I change this to an 8, Now I have 2 times itself 8 times. Times itself another time. That's 2 to the 9th. And now these cancel and I get 2.
I was getting so confused because there's nothing in that
Yep.
first square.
Yeah.
I'm just like, what?
Yeah.
So actually, what do you want me to do here?
So this is what we want, right? We want 2 to the 8th, 9th rooted. That's what we want. And again, this is super easy if you did like the pre-algebra review in Algebra 1 and took it super seriously. But that was literally, I think, what, 3 years ago? So probably don't remember it. And nobody took the exponents seriously or the roots seriously. They're like, that'll never come up again. I don't need to know this. It's okay. So yeah, we need this to be the 9th root of 2 to the 9th. How do we make that happen if we already have 1, 2? Just need 8 more 2's, don't we? Cool. I'm gonna do one more example. Same idea. Let's do 1 because who cares what the top is? Top doesn't matter. Let's do the 7th root of 2. Maybe we'll do 2 more examples. Okay. I'm not gonna multiply by the 7th root of 2 over the 7th root of 2. Because that'll get me the 7th root of 4 in the bottom, which is not a nice number. But if I do this, I get the 7th root of 2 to the 7th. And I don't know what 2 to the 7th is, but what number do you times by itself 7 times to get this? 2. It's gotta be 2. It's gotta be 2. It's annoying how that doesn't fit on the page. 2, right? That's the magic. So one more example. This is the worst case scenario. 1 over the 5th root of 2 to the 2nd. Okay? I'm going to multiply by the 5th root, not of 2, because that only gets me 3 2's, right? I need 5 2's. This is what I want. Is that clicking? Mm-hmm. When I multiply those together, I get the 5th root of 2 to the 5th, which is just 2. And the top is whatever the top is. Okay? Better? Yeah, I don't feel bad. That's going to kick everybody's butt. My goal is that my Algebra 1 kids this year that were reviewing this, because this is technically pre-algebra, right? Technically. No one does pre-algebra like I do, though, right? Because I give you guys, like, absolute hell in pre-algebra. Nobody wants to do that to kids, but you gotta, because you gotta know this. I'm hoping that my Algebra 1 kids that were reviewing this will know it 2 years from now. That's the goal. We'll see. You guys, I knew there was no hope, and that wasn't on you necessarily. That's just how life was for you guys with COVID and everything. All right, so this one, 9th root of 2 to the 8th, 9th root of 2 to the 8th. We get 9th root of 2 to the 8th in the top, and in the bottom, we get 2. Because we get 2 to the 9th inside here. Cube root, or 9th root and 9th power goes away, we get 2. That'll do for now. Do you want to see 1142?
Yep.
I have good news. These are harder, but they're way easier than this one. Way easier, because you need to know less. They're just square roots. Square roots are easy. So I've dotted up this page pretty terribly. I'm gonna just do it here. So looks like you've got 2 over 5 minus root 2. And we want to de-radicalize that. And I'll try to use different colors, but all my big markers are gone, which is sad. Actually, they're in the band room. I should go grab those after this. I'm going to times by not 5 minus root 2, but 5 plus root 2. And here's why. These have 2 terms, right? So when we times them, we have to distribute. Notice I'll get 25. That's fine. That's a regular number, right? No root. So I'll get 5 root 2. That's a problem. However, what will I get here? Same thing, but what? Yeah, it'll be the negative version. They'll go away.
Okay.
Yeah, middles go away. Yeah, no, you're fine. You're fine. They'll subtract and be 0, right? And then this looks like a problem as well, but what is root 2 times root 2? Root 4. And what is root 4? That regular number. So we'll get negative 2. Yeah, that's fine. Yeah. So let's show how this works. 5 times 5, we'll get 25. Love it. That'll be in our bottom. We'll get 5 times root 2. That's not ideal. Positive 5 root 2. Not ideal. However, because we multiply by the conjugate, we're going to get the same thing in the middle twice, except the sign will be different. We're going to get a negative 5 root 2. And yes, those subtract to 0. So our problem goes away. Then we get root 2 times root 2. It's going to come out negative, right? Negative root 2 times positive root 2 is a negative root 4. And that looks problematic, right? But what is the root of 4? It's 2. So we just get 25 minus 2 in the bottom, which is not a problem. That's going to get us 23 in the bottom. That's a rational number. 23 is 23. What's going to happen in the top? Well, it's less exciting, but I'll do it for you. 2 times 5 is 10, and 2 times the root of 2 is 2 root 2. You're never going to get rid of the radical 100%. It's going to be somewhere. We're okay with it being in the top for whatever reason. So there is your final simplified, quote-unquote, answer. 2 you distribute to the top. You get junk, but who cares? As long as the bottom's clean, you're fine. There's probably a joke in there. All right, so that's that. Multiply by the conjugate when you have multiple terms. How you feeling?
Fine, but I have a question about part B.
Oh no.
Could I just add the 1 and the 5 together?
That's a great question. Let me show you why you can't. Imagine I had 1 plus 5x. 5 times x, right? Mm-hmm. Are these like terms? No. No, because one's x's and one isn't, right? So what if I have 1 plus 5 root 3? Do you see how this is 5 root 3's and that's 1, 1? They're not like terms. Okay. So you can't. One's a root 3, one isn't. If you had like 2 root 3 plus 5 root 3, they're both root 3's, aren't they? You can add that to 7 root 3's, definitely. Just like if this was 2 x's and 5 x's, you could add it to 7 x's.
I just have to do what bystanders.
Yeah. No, that's a great question. That's a really logical question. But definitely doesn't work. You know it doesn't work here, so it can't work there, right? But this works for both, doesn't it? Right? Totally fine. They're both root 3's, so how many root 3's do you have? 7 of them. They're both x's. How many x's do you have? 7 of them. Okay? So yeah, can't add them together. Common mistake. They're separate terms. But good news. It's super easy to solve this one. So we have negative 4 over 1 plus 5 root 3. Now, if we times by 1 plus 5 root 3 in top and bottom, we're going to get a middle that's going to have a root in it. We don't want that. So we're going to multiply by the conjugate. Super big brain pre-calculus strategy here is multiplying by the conjugate. Super big brain. You do that all the time to solve problems. So what are we going to get? We're going to get 1 times 1. Totally fine. We're going to get 1 times negative 5 root 3. That's negative 5 root 3. That's a problem. However, we're also going to get the positive version of it, aren't we? Yay, multiplying by the conjugate. It gets rid of the middle stuff. And then when we times this by itself, it's going to come out negative. 5 times 5 is 25. And root 3 times root 3 is the root of 9, which is 3, right? Root of 9 is 3. So we're going to end up with a bottom that is 1 minus 25 times 3. So instead of 25 times root 9, we can just think of it as 25 times root 3. So we're going to get a bottom of 1 minus 75, which is gross, but at least it's a rational number. We get negative 74. So I'll zoom out and let you see all of it in its glory. And what will the top be? Far less exciting. The bottom's the main thing, right? Can we get the bottom to be a regular number? And the answer is yes. Did we change the problem? Nope, we times by a very weird version of 1. How are we feeling about the bottom?
Fine.
You might notice a shortcut. If you know they're conjugates, you know the middle's gone. So all you care about is 1 squared, 1. This times itself, negative 25 times 3. You can just skip to here, right? You know this middle's going to go away. I don't even bother writing it most of the time. The top, if we distribute, negative 4, positive 20 root 3. Again, this is all one term, so that 5 and the 4 get multiplied, and the 3's coming along for the ride. So we end up here. Yada, yada, yada. If you want, you can circle this. Some people will say, that's not simplest form. Do you see how every term here is divisible by 2?
Yeah.
Yeah, we can factor out a 2 from everything and divide out. So negative 2 plus 10 root 3 all over negative 37 is technically the simplest answer, but I really don't care. Do you know to multiply by the conjugate? Can you multiply by the conjugate? Yes. Awesome. Moving on. Did you not simplify your fraction? Yeah, you made a pre-algebra mistake. Welcome to the club. Okay, so those are like the worst ever, but hopefully they feel better. What else can I do for you?
Okay. I don't think I've ever done a problem like this in my life.
Ooh,
but
yay.
11.1.3. Oh my goodness, it's like
11, 1, 3.
11.13. There we go. It looks like this as like a.
Oh, this guy?
I had the, yep.
Yeah. So this is just trying to show geometrically why this is true. So let me zoom in so you can see it. It says when we square this, we get this. Right? A times A squared. A times B times A, we get 2 of them. And then B times B is B squared. So the question is, how does this diagram demonstrate that? Well, the area of, let's do this. The area of this square is A times A. It's A squared, isn't it? That makes sense?
Oh, yep, I see that.
Yep. And I'll keep doing the rest of it. This area right here is B times B, which is B squared. These areas here and here are A times B, which is AB. And the area here is A times B, which is AB. So basically what they're saying is, if you take A plus B, that's what this is. This entire side is the length of A plus B. And you square it. Look what it produces. A plus B times A plus B. That's what this is, right? When you times it out, you end up with a section of B squared. You end up with a section of AB, another section of AB, and a section of A squared. If you add all these together, you're going to get A squared plus 2ABs plus a B squared. That's going to equal the entire thing, right? If you add all those up, you get the whole thing. So that's what happens when you square AB, A plus B. It's weird, but there it is. It's kind of a proof, which is why people hate it. Geometry, shapes class. All right, so there's that. And good news. Do you see how there's no numbers here other than the 2, but the 2 is always going to be there? I cannot change this problem. I might switch the A and the B here and here. It's the same thing. Basically, if you can show me any type of understanding on this, I'll give it to you for free. It's the same thing every time. Cool. All right, what else we got?
What about basically the next page over? It's the compute 41 squared and 49 squared.
So here's how we're going to do this. Okay, I'm going to not do it in my head so you can see what I'm doing. Okay. 41 squared is the same thing as 40 plus 1 squared, yeah? And I know how to do that in my head. It'll be 40 times 40, right? Can you visualize that? 40 times 40. If I were to write this next,
16.
yeah, 16 with 2 zeros. But yeah.
Oh, wait.
Right. Does that make sense? 16 with 2 zeros.
Yeah.
Okay. I'll get 40 times 1 and another 1 times 40. That's 80. Does that make sense? 40 there, 40 there. Right? 40 times 1, 1 times 40. Can you visualize that for real? Let me show you.
Like, yep. I would definitely be doing it on paper.
Yeah, and that's fine. That's fine. I try to word the questions the same way they do for the homework. That way if you...
it's just distribution?
It is. And that makes it way easier than doing this, right? I have no idea how to do 41 squared in my head, but I can do this. 1600. We're going to get 80, right? Because 40 twice. See what I'm saying?
Yeah.
And then we're going to get 1 times 1, which is 1. So 1681 is the answer.
Okay, then the 49,
With some practice, you could get pretty good at this. Do not make this 40 and 9, though. Here's my advice. make it 50
Excuse me, sir.
minus 1. What's up?
Is he dead? Didn't know that I left.
Right.
Door's wrong.
Okay. All right. Definitely going to forget this. All right. So here's how I'd represent it. Because this is way easier to do in your head than 40 and 9. So let me show you what I mean. 50 times 50 is 25 with 2 zeros. You with me on that?
Yep.
We're going to get negative 50 and another negative 50. Negative 100. That's easy. And we'll get negative 1 times negative 1, which is 1. That's better than having 40 and 9, because then you have like 81 and stuff, and it's kind of weird. So we're going to get 2400 plus 1. Plus 1. There we go. How are we feeling?
Pretty good, honestly.
Yeah, okay, yeah. Those aren't too bad. It's just, hey, did you know there's a use for this, for actually computing things, right? It doesn't have to just be variables. All right.
And the last one I hit on this
Yeah.
question is just the one right below it.
One right below it. Okay, good news. This is a difference of squares. I'm going to do the back. Yeah, I'm going to write the answer and see if you can figure out why. 6a squared b cubed minus c to the 5th.
Yes.
Yes. Not halves, but roots. 6a squared b cubed plus c to the 5th. That's the factorization. Do you see if I times this by this, I get 36, a to the 4th, b to the 6th?
Yeah.
And if I times this by this, I get negative c to the 10th, right?
Yeah.
But what about if I distribute? Oh, I'm going to get something really gross, right? If I distribute here. I'm going to get 6a squared b cubed c to the 5th. That's definitely not in the original. However, when I do this, what do I get? Same thing but negative, because they're conjugates. Okay? Let me do a different example. You can see it easier. So if I have 9a squared b to the 4th minus c to the 8th, I can factor this. Three and 3 gets me 9, right? A and A gets me a squared. B squared and B squared gets me b to the 4th. Minus c to the 4th and plus c to the 4th gets me negative c to the 8th. Are you with me on that?
Yeah.
So, love it, but what about this? I'm going to get 3ab squared c to the 4th, right? That's definitely not in the original problem. This times this gets me this. Not in the original problem. Good news. See how these are conjugates? Those middles go away. There's only 2 terms here. There's no middle, right? So I definitely need to factor to conjugates. So what do I need? 3 and 3 for 9. A and A for A squared. B squared and B squared for B to the 4th. C to the 4th and C to the 4th to get C to the 8th. If they're opposite signs, all that middle nonsense that I don't want will go away. Perhaps I should show you a simpler example, because this is an intermediate problem.
Okay, so that was it. Okay.
These are intermediate.
I was just wondering.
Let me show you a simpler one. If I have x squared minus y squared, here's how I can factor this. See other conjugates? X squared, love it. Negative xy, don't love that, don't love that, don't love that, don't love that. However, because they're conjugates, gone. So I'll get my x squared that I loved. I'll get middles that go away. and then I'll get y times negative y, which is negative y squared. Same thing.
But like, what's the factoring part about it?
This is a difference of squares, because we have two squares, square and square. And a difference of squares always factors to conjugates. This guy right here. Sorry, this guy right here. Conjugates. I'm not writing that out. But you get the idea. Conjugates. So what's another example? What if I have 64 minus 49? Yes, you can subtract them, but I could also factor it if I wanted to 8 and 8 and plus 7 and minus 7. Do you see how I'll get 64 and I'll get negative 49, but I'll also get this middle that goes away?
Yeah.
Okay, cool. What about this example? What if I have 64x squared minus 49y squared? 8 and 8, x and x, plus 7 and minus 7, y and y. Are you seeing how that factors? This gets me the 64x squared.
So basically, don't worry about what's in the middle because it's gonna.
It's gonna go away because we have conjugates. That's the beauty of conjugates, right? We're gonna end up with 56xy. That's negative 56xy, right? From here. Here, sorry. These guys will be negative 56xy, but this will be positive 56xy. Gone. Who cares? Gone. And then we get negative 49y squared in the end. So, yep, totally works. What about another example? What if it's not 64 and 49, but it's something like this? A to the 4th x squared minus b to the 8th y squared. This is a difference of squares. A squared, x and x, plus and minus, whoops, plus and minus, b to the 4th, y and y. And we can check it. A to the 4th x squared, love it. Junk, that's negative. Same junk, that's positive. Awesome, they go away. Negative b to the 8th y squared. Same thing. So now, are we ready to go back to that original one? We're going to find out. 36, a to the 4th, b to the 6th. Oh, that's a lot of junk there. Minus c to the 10th.
Would it be plus and minus or just?
Has to be conjugates, so it will be plus and minus.
Okay.
Plus c and minus c to the what? 5th. Does it work? This times this gets us that. That's why you came up with it, right? These two multiply to that.
Okay, I just thought that there were like 4 different terms. And it was just like,
And it would be a nightmare, right? It's
Yeah.
not that bad once you see it, but seeing it's the hard part sometimes, right? Hold on. I gotta text Abigail and tell her. Remember, I have review tonight. Oh, and I have an email reminding me to write your sister a letter. A above the rest. Okay, cool. Sometimes I send myself reminder emails that pop up later. Abigail. Okay, cool. Can't believe I got service here. So this next one that's right next to it is super easy. It's 2x squared minus, not 8, 4, because we're going to multiply these, right? 4 times 4 is 16. X cubed y squared, x cubed y squared. And they got to be conjugates, right? Boom.
okay.
Better?
Yep.
Yep, they all multiply. They all multiply. Yep. Cool. Not so bad once you see it. All right, what else do you want?
Hold on.
Yeah, take your time.
quadratic formula.
Okay, so which one?
So 13.31.
1331. Okay. 1331. Yep. Yeah, look, Joey wanted it too. Right. Okay, so just using the quadratic formula. All right, that's actually not too bad, but yeah, I don't blame you. It's also kind of gross. So I'm going to not grab another one of these to save time. Instead, I'm just going to like write down in big marker what's going on here. All right, so we have this quadratic equation, which is not factorable. Could we complete square? Sure. It'd be kind of gross because there's a 5 here. We could have to get 5 halves, but like it's not bad. There is a formula. It's, I don't know. It's fine. It's fine. You need to know it. And the formula is this. Your x's will always equal negative b plus or minus the square root of b squared minus 4ac all over 2a. And by the time you've memorized that, and by the time you've plugged all your numbers in, and by the time you've calculated it out, completing the square probably would have been faster. But you need to know it. It's all the rage. So, to be clear, our a value is 1. Our b value is 5. Is that tracking? We're good with that? We understand what that means? C equals 1? If not, that's okay.
No.
Oh, good. That's so easy to teach. Okay, so when it's in standard form, do you see how my x squareds are all together?
Yep.
See how my x's are all together? See how my constants are all together? It equals 0. When it's like this, what is the coefficient of my linear term? 5, that's b. What's my constant? 1, that's c. What's my constant, or my coefficient of x squared? See how there's no number here? That's 1x squared. That's where the 1 comes from. If there was a 2 here, I'd write a 2.
Confused on why a was 1.
That's the one that gets everybody. Yeah, there's 1x squared. I have 5 x's and I have 1 constant, right? That's it. So now I do this super fun thing that most math classes consist of only, which is plugging in numbers and seeing what you get. God, if that was all math was, I would not be a math teacher. What a waste. But it's okay, we can do it occasionally. So we're gonna plug in 5 for B. And we're gonna plug in 1 for A, which is what we like to see. Makes the problem pretty simple. And we're gonna plug in 1 for C. And then we're gonna calculate my least favorite part of math. So how do you feel about there's a formula, you plug stuff in?
Oh. My God, that's okay. So that's why I've been stressing about this.
Yep. So you're gonna need to know the formula, but you get to use your stuff.
Oh my God.
It's okay. Literally everybody that meets with me, which is not very many at this school. It used to be like everybody. I don't know, something's weird about this school. They would come in and go, oh my God, that's it? Just for every single problem. And I'd be like, yeah. It's okay. I love you all. So if we just like do stuff, we end up with this, right? Negate 5. Okay, it's -5 now. Square 5, 25. Okay, subtract whatever 4 times 1 times 1 is. Subtract 4, okay. Here's our answer. And it shouldn't surprise you, it's gonna be an awful one. I told you this last one wasn't factorable. So we get the square root of 21 over here, which is not nice, all over 2. Ta-da! There it is. That's it. You plug in the numbers. But you gotta find the numbers first. So for instance, this one right here, C is not 10. It's -10. You gotta rearrange it, right? Okay, second thing. Sometimes they're mixed around. You gotta rearrange it. Okay? And then you can find out what A, B, and C are. Sometimes A isn't 1. Sometimes A is like 7, and you have to plug in 7 instead of 1 for A. I don't know. I don't know. That's it. How you feeling?
Not horrible.
Good. Not horrible's good.
Making those folders a lot.
That's why I'm here. Anything else?
No, I gotta go.
That's cool. All right, so everybody watching online, that's it. That's all we got time for. I didn't go over much of the basics because the people who came in didn't need the basics because they're actually pretty good. So I guess we'll cover the basics in class. God help you all.